Next up on the roster is Chris Neugebauer, who's perhaps well known to many of you as a frequent serial organizer of conferences here in Australia. He hails from Tasmania, but now he lives in the United States, in California, where he serves as a director of the Python Software Foundation, and also is a co-organizer of a small boutique conference called North Bay Python. He's here to talk about blocks and where they are or where they hide in Python. Please give a hand to Chris Neugebauer.
Hello, hello, hello. Yes. Do I have a mic? I do have a mic. This is Fantastic Blocks and Where to Hide Them. My name is Christopher Neugebauer. And for those of you who were here last year, you'll recognize this as the second in my series of talks about design patterns in Python. Just a first warning, this talk will go to time, and because of that, it means I'm going to skim over some unimportant details in some of the stories in this talk. If you notice a detail that is missing that you desperately feel you have to point out, don't. I'm skipping over because it's not important. So today's talk is about anonymous blocks. Blocks are a feature that was last seriously discussed in Python in 2005, is not seriously being discussed right now, and is unlikely to appear in Python anytime soon. So thank you for coming. Right, so I've only got 30 minutes. Why am I talking about something that is not relevant to Python? Well, here's a quick summary of my biography, and if you were to ask me to summarize this biography, you would note that I do a lot of things that are Python, and I often do a lot of things that are not Python. Not writing Python means I spend a lot of time thinking about how the things I do in Python are different in the language that I'm currently using. These days in my day job, that is Kotlin, which is a really neat JVM language. In the past, it's been Java 8. There's been a tiny bit of Swift as well. These languages are object-oriented languages by default in much the same way that Python is. But they're also great examples of languages that have adopted functional style APIs where it makes sense to do so. That is to say, they encourage passing blocks of code around. Now, when I first used Python, which was 15 more years ago at this point, it stood with Ruby as one of two mainstream languages of the time that encouraged this blend of functional style design alongside OO design. But these days, Python is far less interested in functional style programming. And this shift really started at the turn of this century. Started around 2001 when they introduced the list comprehension, and that was followed by things like generator expressions and generator functions. These were basically all features that made functional programming, in the direct sense that we understand it now, far less favored in Python. So by the time 2005 came around, Python had really squarely moved away from this passing code around idea and towards providing syntax to accomplish similar results. And this brings us to the discussion of blocks. So first, let me just explain what I mean when I'm talking about blocks. So Python has two ways to define executable bits of code. You can define a multi-line function. In Python, a multi-line function must be assigned to a name. You can also define a lambda, which may be anonymous. It may be passed as an argument to a function, but it may only be one logical line long. So this becomes awkward when you want to pass around a multi-line function as an argument. You sort of have to define that function, you have to give it a name, and then you call the function that accepts it as a parameter after you've set it up. This is quite roundabout compared with how other languages do it. For example, in Kotlin, the multi-line example looks as natural as a single line example would. So we can conclude from this that interfaces that expect blocks are not Pythonic. So today, we're going to look at how Python's design choices have evolved some parallel patterns to the block-style patterns that have evolved in other languages. And then we're going to look at some cases where Python's design choices have kept Python from keeping up with languages that support blocks. And then we're going to show you how to contort Python to support these features in generally inappropriate ways. And I hope that we'll answer a couple of questions. Get some insight into how Python is keeping up with these modern design patterns and the evolution of programming in places that aren't Python. And we'll even answer the question as to whether Python is able to keep up with these design patterns. So we're going to start with the case that informed the last discussion core Python had around blocks. This was in 2005, which was a really interesting year in Python's history. It was the year after the two most important web frameworks of that decade were released. Now, we all in this room would know that Django was Python's real entry into that battle. The competitor, surprisingly to many at the time, did not come from PHP. It came from Ruby, and Ruby on Rails in particular. And Ruby has a really interesting outlook on how to do programming, especially if you compare it with Python. So Python has explicit loops and iterators and those sorts of things. Ruby strongly encourages people to do things with anonymous blocks. So the for each loop that's common in Python, it's common in many other languages, it's implemented in Ruby by convention on container types. This is a philosophical difference between Python and Ruby. Either one of these approaches is fine. But there was something that Ruby could do that Python couldn't. This is how you would write to a file in Ruby. There's a method defined on the file objects that ensures that the file is safely opened before writing and safely closed after you move on. And if you're a Python developer, this would have seemed very, very strange to you at the time, because this was the absolutely correct way to write to a file in Python. You needed to correctly set up a try finally block. This is kind of awkward. You need to define a variable outside the scope where you start using that variable, and then you have to remember to do the right things in the finally block. And this approach to getting people to write code is like putting up a sign telling people not to fall over where there's a slippery floor, right? The floor is slippery, people will fall over, but you might feel nice that you've told people not to fall over. People still fall over. It's actually worse than that. This try finally design meant it was easier to do the wrong thing than it was to do it properly. This is how I would write code that wrote to files before Python fixed this. The right way to do things, the try finally statement, was not obvious. So file system operations, concurrency locks, a lot of things like this led to a series of enhancement proposals being proposed in 2005. And one of the PEPs proposed something that looked like this. It said it would be easy with some syntax to write a with function that took a block of code that would be run in a context with setup and teardown performed correctly on either side. This PEP, however, that would make it easy to do that, was not adopted. And it wasn't adopted because it would need some general syntax to create what in the Python world was known as a thunk. Now, a thunk is some code that is saved for execution later. Thunks are what we now know as anonymous blocks in other languages. And Guido thought that thunks created ambiguous expectations about what code would do. He said, I think I'd be slightly uncomfortable seeing a block and not knowing whether it will be executed in the normal control flow. And the result of all of this was that we got the with statement. The with statement is a piece of syntax that keeps your main block of code in line within the calling context, but it delegates the setup and shutdown in a predictable way. And this differs from Ruby, where the setup and teardown are part of the main control flow, and the block gets saved for execution at some point in there. It's basically by convention that the in-context block gets executed locally. It's convention, it's not a requirement. And this convention approach is a very standard pattern in Ruby. Ruby uses blocks in a certain way, and people make the language easier to use by handling blocks in that way. The expectation is that if you see a block, the control flow behavior will be obvious by looking at the calling context. Python's model, on the other hand, opted to come up with a syntax approach that encoded the correct way to do things. The with statement did away with an option that relied on convention to work properly and replaced it with something that maintains predictable control flow. And this was understood as a thing at the time. The Zen of Python said there should be one, and preferably only one way to do it. Now, not adopting blocks in 2005 proved prescient in another case. The year is 2006, Python 2.4 is current and has generators. Generators proved to be a great way of factoring out iteration patterns. Now, after people had played with generators for a while, people realized that generators looked a bit like coroutines. Coroutines were this idea that everyone thought would be revolutionary in the 70s, like it made it into Knuth's books. But by 2000, everyone realized that concurrency could be handled completely automatically without issues by using threads. So manual concurrency models were not considered to be important. But to placate the people who had read Knuth, Python 2.5 added some more syntax to generators to support actual coroutines. Specifically, they added this assign to yield syntax, and this means that you can now return some value to a calling context, pause your execution until it's called on again, and then receive values back from that calling context into your coroutine. This sort of pattern is the building block of non-blocking I/O, and it does it using coroutines in a way where the control flow, if you look at the code, is linear and easy to understand. In Python, coroutines were still really awkward to use in practice. They relied on concepts from iteration that make sense when you're using a generator and a for loop, but they don't make sense if you're using them outside of that context. Like next and stop iteration was still dealt with. And David Beasley, he gave a tutorial at PyCon a couple of years later on generators, and he concluded in his final slide, most programmers do not really understand generators yet. So 2008, we have a great syntactic and structural approach to doing non-blocking I/O that literally nobody understood how to use. In 2009, something remarkable happened in the JavaScript world, however. This thing called Node.js got dumped on the JavaScript world. Node.js, as originally planned, implemented non-blocking I/O using blocks that would represent callbacks that get run whenever an otherwise blocking function got finished. And this solved the sort of concurrency issues that web programmers actually faced, but they were solving with threads at the time. And it turned out that doing things asynchronously like this was very, very, very fast, especially in comparison with the threads that people were used to. But the problem with using blocks in this case is that handling sequential operations tends to get really unwieldy. Like this is a callback block here, and if you want to do something after that callback block gets executed, well, you need to put in another callback block, and you want to do things sequentially, you start nesting things, and your code goes like this instead of like this. It's very hard to read, especially if your terminal is narrow. So we agree as Python people that blocks look terrible. Blocks looked terrible, but nobody understood coroutines, so people went to blocks because they could at least understand how they worked. And it wasn't until 2014 that Python seriously considered using coroutines as a way to do non-blocking I/O. We got async I/O, this suite of async I/O routines based around coroutines. This was like 6 years later, despite coroutines being impossible to understand 6 years ago. It still had some weird generator syntax, like yield from doesn't make much sense. And there wasn't like syntax to say that something was a coroutine. You had to use a decorator. So Python 3.5 added some syntax to make it clear that there was async stuff going on, and then it used syntax to encode structure so that you could tell that async stuff was going on. Like if you see async def, you know that it's async and you can only call await on async functions. These were enforced by the language. This syntax worked really, really well. Async I/O was reasonably good, and the syntax was so good that JavaScript immediately adopted coroutines, and it immediately adopted the async await syntax at almost the moment that Python proposed it. So by not having blocks, Python rekindled this idea from the 70s. We got intelligible syntax for doing non-blocking asynchronous I/O, but it took 5 years. We lost a syntax advantage that we had from before Node even existed, because the library support wasn't there. So we kind of donated a great way of expressing non-blocking I/O to JavaScript. Hooray! So let's take some stock. We have learnt that Python values linear control flow, and Python doesn't have anonymous blocks because they allow control flow to become non-linear. We've also learnt that Pythonic ideas tend to migrate out of Python. And we've also seen before 2010, Python tended to find better design patterns because it didn't have support for anonymous blocks. But what's happened with languages with blocks have grown over the last 10 years. Let's look at how a pattern from the 1990s has developed. This is the Gang of Four book on design patterns. It introduced a whole pile of design patterns that made it easier to structure your software within the feature set of the object-oriented languages of the time. These languages looked a lot like C++ and Java, primarily because they were C++ and Java. One such pattern is the Builder pattern. Now, the Builder pattern shows how to use object orientation to construct free-form hierarchical data structures. But people who discovered the Builder pattern through Java following that found that it was a great way to work around the fact that Java does not have optional parameters for constructors. In essence, people would use the builder pattern to build single flat objects rather than hierarchies of objects. And so if you look at how people use builders in Java that way, and then you look at Python, well, you go, we have optional arguments. And what this has meant is that people tend to look quite unfavorably upon builders in Python. I did as well until I read Brandon Rhodes's Design Patterns book. He has a great chapter on builders in it. He shows examples from the sciences and the standard library that use builders. Now, Elementary and Matplotlib are both examples of libraries that present a builder interface to producing their underlying data structures. So here's an example of a builder library for building some HTML documents. So as we know, HTML documents sort of look like nested tree structures, so you can use nested builders to build each subnode of a tree. It's not until you call build on everything that it outputs the data structure that you actually care about. So that's the interesting thing about builders. Builders themselves are not particularly important at all. Builders are an intermediary towards getting a data structure that you want. What you really care about is having a declarative way of building up your data structures. So, say you have a function like this. It's a function, it takes a tag name, it takes a block. If you've got something like that, you can create a builder object behind the scenes, you can run a block that accepts that builder, and then you can call build on it. You abstract away the setup and the teardown of the builder, leaving the way that you declare the structure to the programmer. And this is what that would look like in Kotlin. This looks like a description of an HTML document. And as Python developers, I think this is the sort of thing that would feel right at home in Python, because we're already used to using list and dictionary literals to build up our data structures. We use our language to describe data structures. What these implicit builders give us is a way to describe any data structure in code. So it would be very nice if we could do this in Python. Can we do this in Python? Well, let's start by making a builder class. We're going to take a tag type as a string, and we're going to store a list of child elements. And because it's a builder, we need a build method that just outputs the HTML of that particular tag. This is a builder. So we're going to add a way to add some text to one of these tags. Just add an add text method, add some text, great. And we're going to optimistically add a method that takes a block and uses that to build a child tag. Now, obviously, there's no support for blocks in Python, so there is no way at all that this would work. But because I'm ever an optimist, I'm going to write a caller function that also takes a block so that we never have to explicitly touch a builder. So we have these two APIs that require a block. How would this work in Python? Well, it turns out that the signature for a function that accepts a block is exactly the same as the syntax for decorators in Python. So you can go at markup on top of a function, and that would cause something to get executed. And that means that you can define an HTML document like this. Each tag is built up with a nested function. Okay, and it produces some HTML. What's weird is where this HTML document string gets stored. What we thought was a function definition is actually defining an HTML string. Using that markup decorator is what causes that builder to get invoked. And a decorator stores whatever the decorator returns as the name of a function. It doesn't actually have to be a function, it just needs to be the return value from a decorator. So we have working implicit builders using real Python syntax. Is this good Python?
Yes.
Let's ask the Zen of Python, because the Zen of Python knows everything. If the implementation is hard to explain, it's a bad idea. This is obviously hard to explain. We've hijacked the def keyword to store things that aren't functions. If you looked at some code that used this thing, you would not know what was going on. But there's a bigger point here. Python is in favor of syntax to indicate the shape of control flow, as Guido suggested when rejecting the with function. So now I find myself asking whether or not decorators at all are Pythonic. After all, we've just seen that applying a decorator to a function doesn't even guarantee that you'll have a function after the definition is completed. The answer to me is that decorators work because there is a strong convention around their use. But as we've seen from Python's development since 2005, we do not like relying on convention for things. I've found this very confusing, and I'm sure you have as well. So I'm going to finish with a discussion of tools for error handling, because errors are a fact of writing programs. Now, it's fair enough to assume that errors don't always have to be catastrophic. Errors can be like transient recoverable network errors. It could be like difficulties with primary keys or those sorts of things. It could be a halt and catch fire sort of situation, but generally they're often not. But Python only really gives us built-in tools for handling the catastrophic variety of errors. So to inform this discussion, where it's going to say I've got an application, it takes a request to create a user, calls some internal API to create it, and returns a success or a failure response. Something like this. They're different sorts of responses. That's the important bit here. So if we assume we're never going to handle the failure case, well, this is what our code would look like. We go create user, then we go create response, and everything is fine. Here it is once you handle the error using Python's built-in tools. The code actually starts looking kind of terrible. And this is because you have to sandwich the error handling in between the two lines that handle the success case. So the error path here, the thing that's infrequent, is easier to read than the success path. This is called poor code locality. This is where two bits of related code live visually far apart. Now, what if we wanted to do something with our response after it's created, regardless of whether it is a success or an error? You'd rearrange your code to look like this. And this actually improves the code locality. But then what if this bit causes an error here? It's kind of hard to tell which bit of the try block is going to be responsible for this exception being raised, unless your naming is really good. And as we know, naming is one of the 3 hardest problems in computer science. So what you could do is abstract away the bit of code that causes the error, and then abstract away the functions that create the responses. But now you've got to like jump around and look at various different function declarations in order to figure out what's going on. So by making your error handling correct, you've made your code locality even worse. So we can fall back to using if statements here. But if statements are kind of ugly as well. We're relying on defining the same variable inside both branches of the if statement, and then we test that variable that we've created one level up. And we're also relying on convention. Like, seeing an if statement doesn't say, this is error handling logic. It just says that we're branching. So perhaps there's a structured way to do this. So the functional programming world has a thing called an either type. An either type is a type that can hold either of 2 types of values. For example, a success type and an error type. If you've played with MyPy, for example, you would know this as a union type, but I know it as an either type, so that is what I'm going to be talking about. Once you have an either type, you can perform an operation called fold. Fold takes a success handler and a failure handler and will run the applicable one for the value that you have, and it will return a common value type. So if you recall, this is our unstructured Python example where we're using an if statement, and this is a structured version written in Kotlin. And this is nice because we give both the happy and the unhappy paths equal code locality, and we assign this response variable just once. But this is an application of convention, and as we know, Python does not like us to rely on convention. So we would rather see some explicit syntax for this, because syntax guides us to understanding control flow. So the functional programming world has an example, has a thing for this as well. It's called pattern matching. Pattern matching is a structured way of using types to determine which code gets run. So in Kotlin, that looks like this. Use a when statement. It doesn't do the same thing as the Python with when statement. It's like a switch. But you provide a block for each type that you want to handle. Each of these blocks for the types returns a value, and that gets assigned to a common assignment statement. So you get excellent code locality. You assign your variable once. It's lovely. So could we do pattern matching in Python? Well, that would depend on us deciding whether or not matching types is Pythonic. And, well, we know with the big discussion 4 years ago that types will always be optional, should never be a thing we rely upon. It's not a Pythonic thing. You use it in a limited number of cases. But what if all your return types were to inherit from base exception? You can throw your return type, and all the except statements are just pattern matching operations. So Python has pattern matching on types built in, provided you inherit from base exception. And this was something that was made worse in Python 3, because in Python 2 you could throw literally anything. So there is a restricted set of pattern matching operations in Python 3. You just need to make all of your APIs, your return types, subclass base exception, which is totally readable. But that has the same problem as the if statement. We're redefining variables everywhere, and that isn't very neat. So syntax doesn't work with Python at the moment, so let's fall back on convention instead, and let's try and implement fold. So let's define a folder class with a way to register some functions to it, so you can register our handlers. And of course, because we need to fold things, we're going to add a fold function in here. It takes an either thing or will run one of the things we register. Then suddenly you can call fold like this. You define a folder, you register a couple of handlers, and then you call fold at the bottom of it. But then we've got this builder-like thing that we're dealing with explicitly, so let's deal with that implicitly. Let's wrap it up in an outer function, and then we can invoke that function using a decorator, which means that we've just implemented the fold operation using decorators and implicit builders. At this point, I found myself extremely confused. Why did I find myself extremely confused? Because in my research, I had learnt that Python is in favor of using syntax to indicate the shape of control flow. But then if that's the case, what if I were to define a function which has a couple of callable parameters, a couple of non-callable parameters as well, just to make things interesting, and then I wrote code that looked like this? So we've got a caller, we have some arguments that are not functions, and then we decorate some other arguments that are functions. Some of them we assign with keyword arguments. And then a decorator stores the result of calling that function, which is to say that Python gives you syntax that lets you call a function by defining a function. Decorators not only rely on convention to be used properly, but they also let you completely invert the expectations of all of Python's control flow. In Python, with normal syntactic features, you can call functions simply by defining those functions. Sorry. So before I conclude, some observations. There are some Python constructs that are much nicer than blocks. We saw that with the with the with statement, and we saw that with generator-based coroutines. But then we saw that there are some important design patterns that have been emerging over the last few years that don't have good analogs in Python. Then we accidentally saw that Python supports throwaway blocks by using decorators. So maybe we should just make decorators use what people expect, make it so that decorators only do what people expect them to do, and come up with some better syntax for all the rest of the ridiculous stuff that I just showed you. Thanks to Steve Dower and Nick Coughlin, who helped me develop some original ideas, made sure the implementations weren't entirely terrible. I'm running a Python conference in California in November. Our CFP is open. If you're interested in speaking at that, you should definitely submit a talk. The CFP closes on Friday. This has been Fantastic Blocks and Where to Hide Them. My name is Chris Neugebauer. You can tweet me there. Thank you all for coming along. You can find me in the hallway after this to tell me how terrible I am.
Usually the mug is a thank you for your talk. I'm not so sure in this case.